All right, so there's several topics sort of rolled into one here. The big letters tell you I'm going to talk about learning curves, but I also want you to think of this as a way to scan some parameters for a machine learning algorithm. And we're basically going to treat the training set size as a parameter in some of these scans. And so when we do that, that's a learning curve. So this is what a learning curve looks like. It's a plot of performance over experience. All right, so on the y-axis, we have some measure of error. And the x-axis is the training set size, or the number of examples that the algorithm has been trained on. Now I'm showing two kinds of error here. The red bar on top is the test error. So this is the error evaluated on data that the algorithm has never seen before. And the blue line shows the error on the training set. Now this particular diagram was done on simulated data, where I know exactly how much signal and how much noise I have in this data set. And I know how much noise I put in. So I know that no model should ever be able to predict that noise because it's random. And I can draw that noise. That's the level of error that's supplied by just this random noise that I've added. So I know that any model that's better than that dotted line is too good to be true. And normally, the only way I can ever get better than the dotted line is to overfit. And that's what we're seeing here. The blue lines are all too good to be true because they're overfitted to some extent on this training set. And the red lines are all above the irreducible error in this set. But the more data we train it with, the better the performance is on this held out test set. OK, so we have to take a little bit of a digression here because I want to talk to you about the problem I'm going to illustrate this on. But before we start the digression, we have to do another digression because I need to start the big job running on the cluster so it can run while I talk to you. So I'm going to take the same job that you're doing, that you'll be doing for your hands-on part, only I'm going to run it on a full cluster, and you're going to run it on a single node cluster. So I get more nodes than you do. So I've got two different browsers logged into two different RStudio server instances running on two different virtual machines. Or one's on a virtual machine. This one's on a virtual machine just like yours. And the other one is running on the edge node of an HDInsight Spark cluster. But they both have the same code in them. All right? So I'm going to load this R Markdown file called gibberish HDInsight RxFest linear. And all I'm going to do now is just start it running. So it's an RStudio R Markdown file. And when I push run, I
detect gibberish.
Yes, I think I just got some gibberish. Famous last words. Nope. Oh, sorry. It's doing control clicks. How do I? It looks like control is stuck.
It's an R Markdown file. Isn't it like run the comments?
No, I want to run the whole. Oh, sorry. I need to push knit. That's what I want.
You got it?
Yep, I got it. I was just pushing the wrong button. All right. So this is going to take about 10 or 15 minutes to run. Meanwhile, we'll go back to our slides. OK, so I want to talk to you about my toy problem here. So this toy problem we're going to solve is inspired by an actual problem that somebody brought up, which is they're running a website where users can download some software. And the marketing department wants to collect the user information for everybody who downloads the stuff from the website. And the trouble is when you do that, people are going to put in garbage names. They put in a name that's not their real name. Probably not even a real name at all. So they want a machine learning or some kind of system that will filter all these things out so they don't end up giving the marketing people a bunch of bogus names that they have to call. Okay? So the real problem, they have a lot of information from the form, which will be first name, last name, email address, telephone number, the company you work for. And they want to know if any or all of those are fake. But for today's exercise, we're only going to consider first names. Now, I say it's a machine learning example inspired by that problem because I don't think that what I'm going to show you is actually a solution to that problem. If you think about it, this may not actually even be a machine learning problem. Because if you can imagine having a database of all known first names, then it's just a lookup problem, if that were really possible. If that weren't possible, then maybe you would have to do machine learning on it and try to generalize. And the reality is probably somewhere in between there. But I'm not looking for reality here. I'm looking for a machine learning problem. So I'm trying to build a problem that's inspired by this where we are definitely going to generalize and we're going to make a machine learning problem from it. So this is the data set that I came up with. So I took the baby names database. It comes from the US Social Security Administration and has all the registered first names of American citizens who registered with Social Security since about 1890. And I just took the name column out of that, and I took only the unique names. And there are about 95,000 unique names in that database. And I held out a test set. So the test set has 20-something thousand names that are guaranteed to be different from the 71,000 names that are still in my training set. So again, this is not supposed to be realistic because in a realistic problem, you have names that are much, much more common than other names. So you'd probably want to bias toward the common names, get really good at that. But I'm actually doing a harder problem because I want to generalize from one set of names to a completely different set of names that I know that the algorithm has never seen before. Now, I want to distinguish these from gibberish names. Now, I don't really have a good source of actual gibberish. So I had to make something up. So I made two kinds of gibberish. The easy thing to do is just to randomly select letters from the alphabet. But really, very few people randomly select letters from the alphabet when they fill out a web form. They're more likely to just mash on the keyboard. So I did a very superficial study of what it looked like when I mashed on the keyboard. And then I wrote, because I didn't want to make like 700,000, I didn't want to mash 700,000 names myself. So I mashed on the keyboard for about half an hour, and then I looked at some character distributions, and I wrote this little function to make some data that kind of looks like that. And basically what it does is it knows where all the keys are on the keyboard, it knows where the home keys are, it knows the keys that are most common in my key mash gibberish, and it'll pick a place, and then it'll scan back and forth on the keyboard a little bit, and then it'll jump somewhere else and scan back and forth on the keyboard, and jump somewhere else and scan back and forth on the keyboard. So two kinds of gibberish. So this is all there is in the data set. We've got the name column. I keep that label of what kind of gibberish it is, just for my own amusement. But the real outcome that we're going to use is just yes or no, Boolean, is this a real name or is it not? So how do we train a machine learning algorithm on that? We have to come up with some features to train on. So I'm going to be showing you the inline text featurization functions in this algorithm, RxFastLinear, from the Microsoft ML package. So you notice that this is the call to fit the model. We're giving a formula to this model, and the outcome is that Boolean column is real. But the input is a column that doesn't exist yet. The input is called kgrams. And that was not in our data set. that's going to be generated on the fly as this data is read in. And it's going to be turned into a vector of charactergram frequencies according to this transform function that we're going to pass in. So we're going to call this we're going to supply a function to this ML transforms argument. And that function is featureized text. And that featureized text is going to generate a new variable called chargrams from the name column. And then I'm specifying everything I want it to do. So first of all, I want it to turn everything in lowercase, because if you were to look back at the data, the real names are properly characterized and my fake names are not. And so it's like totally too easy to tell the real names, because they're the only ones that start with a capital and only have the first letter capitalized. So I'm just going to turn everything to lowercase. Similarly, only the pseudo gibberish names have numbers and punctuation and stuff in it. So I'm going to tell it, don't keep that stuff. Don't keep diacritic marks. Don't keep punctuation. Don't keep numbers. And now I have to pass that a function that says how it's going to keep track of the engrams. And one of the attributes to that is the Engram Length. So in this case, I'm telling it to make engrams up to 3. So what that means is it's going to take every character 1 at a time, 2 at a time, or 3 at a time, and it's going to build a table of features for that. And this is all done. I don't have to do it myself. And I don't even have to expand that out into memory, because this is going to be a very sparse feature set. So if I had to actually write out all those zeros, it would turn this into a bigger problem than it has to be. But this handles all this sparse feature tracking and everything for me. I never have to mess with it. So that's what that function is going to do. And when we get the fitted model, it's a linear model that was trained with a stochastic. It's actually dual coordinate ascent, and it has coefficients like any model. And this is what the coefficients look like. So these are coefficients of 1, 2, or 3 letters. It also has the beginning of the word marker, so that's considered another character in this set, and the end of the word marker. So now let's go back to look at the code. And you can bring this code up in your own browser and follow along. Yeah, so this one is pointing to my single node cluster. And I'm just going to talk about and run each of these chunks in order. Oh, I'm sorry. Let's see. Sorry, borrowed computer.
In the zip file we downloaded, is it part of the
You can do the,
I think I just closed it.
you can do this. Oops. And,
I think if I change back, it should,
works.
yeah, that worked. Okay. I'm sorry, question? No question? All right, so the files we have here, let me just talk about that. They're in the code, they're in learning curves. So you should only have 4 files to start with. I'm going to delete everything that you don't have, because we regenerate all that stuff. Okay, so the 4 files you have are the data files, are these XDF files. So that's the data file format for the Microsoft R server. It stands for external data frame. So all of these algorithms are designed to work off disk instead of in memory. Or at least they can work with these files. So there are 2 of those files. There's the test data, which is 3 megabytes, and there's the training data, which is 10 megabytes. Then there's a library file, which defines this function that I wrote. that basically treats training set size as a parameter. So it wraps your learner in another function that takes training set size as a parameter too, so that we can run these scans over different training set sizes. And the file we're really going to look at is this gibberish HD inside RxFS linear file. And that's the one I have up in the editor. Okay, so that first block just sets some environment variables. And then we start in the second block. So there are a couple options, flags that I wrote that control where all this computation is going to happen. So the first flag determines whether or not we're going to use Spark. So the option to using Spark would be to use your local machine. Now, since you're running on a virtual machine that does have all of this, all these packages installed, you could set that to false, and it would run on the VM, but not use any of the Spark stuff. But we'll leave that set to true, which means that it will run on that data science virtual machine, but it will run in the Spark single node cluster mode. So you're pretending you have a cluster, and you actually do have a cluster, but it's only got one node in it. The next flag, use cluster, means do you have a real cluster or not? So I have a real cluster and you don't, so you want to leave that set to false. And then I have another flag that we're not going to mess with that just controls whether or not we use HDFS. Because if we weren't using Spark, we could use the local file system. So the first thing we'll do here is go through and set up the HDFS. So we have these files that are in the local file system. And if they're not in HDFS yet, we have to copy them over. So that's what this code does, and it's controlled by that use HDFS flag. Now again, the path on the HDFS depends on whether you're using the single node or the real cluster. So we set that appropriately. Then we take the full path to where we want to put the data, and we wrap it in one of these RxXDF data objects. So that's going to tell us that we want to have an object that points to that location on the distributed file system, and it's going to create a composite set of files on HDFS. But it doesn't exist yet, so we're just pointing to where we want it to be. And we do that for both the training set and the test set. And now we go through and see if that file exists. And if it doesn't exist, we have to create all the directories to where we want to put it, and then we have to copy the data from the local directory into that directory. Okay, so that's what that chunk of code does. So if you haven't run that yet, just be sure you run that block. And the first time you run it, it actually has to copy that stuff into HDFS, so it might take a minute to do that. And it's going to set these two variables to be pointers to where the data is. So if we were not using HDFS, then these pointers would be to files on the local file system. But since we are using HDFS, they'll be pointing to files on the distributed file system. So the training data is in this object called data table. And the test data is in an object cleverly named test set. Now, I didn't call it training set because we're going to actually be pulling training sets out of it. Remember, we're not necessarily going to run the whole thing. We're going to run samples of it. And we're going to see how adding more and more data in affects the learning. Okay? So the whole set is called the data table. And then we're going to be taking training sets out of that. But if we want to find out what that data looks like, we can run this rxGetInfo object on it, rxGetInfo function on it. And that will get us the sort of the summary information about everything in that file, so the metadata about it. So it tells us, for example, that we have 1.49 million observations in that file. It only has 3 variables, and those are the name, the category, and the Israel variables. Okay, so before I show you the learning curves, I want to just fit one model at a time, just so you can see this work. So when we run this chunk, it's just going to run the code that I showed you in this slide earlier. So it's going to call the RxFast linear learner on all the data in the training set. So we're going to do it on the whole thing using this formula where the inputs are from this caregrams feature that's generated on the fly by the featureized text function. So it's doing all that stuff that we talked about. And that took, on this box, it took 17 seconds to do that. So now we can examine what that model does. So I'm taking the test set and using the RxPredict function on it to run that model on all the cases in the test set. And I'm writing the results out to this XDF file to store in this function called predictions.xdf. So that's one of the files that shouldn't have existed when you first started here. And it will have appeared here, this new file, about 13 megabytes of predictions. So we can take those predictions and do some cross tabulations on them. And so all the results from that chunk are now written sort of notebook style underneath it here. So it took the predictions and generated a ROC curve. Oh, sorry. Yeah, there it is. Let me make that full size. All right. So remember, it's trained on a training set that has unique names in it, and it's tested on names it's never seen before. And we're still getting this ROC curve that's to 3 significant figures, the AUC is 1.00. So yeah, it works really well. This is not memorizing, it's not overfitting, because these names are unique. But let's just look at some details just to convince ourselves that it's really discovered something about the naminess of a name. Right? There's some characteristic that names have, and it's able to recognize that. So that's where we go back and do these tabulations on it. So the first, let's see, the very first block is just a tabulation on everything. So it shows that we have, in the test set, we have almost 250,000 pseudo-gibberish names, almost 250,000 random names, and 2,700 real names. Oh, I'm sorry. No, this shows the cross-tabulation. How are they predicted? So this is just whether the prediction probability is over 0.5 or not. All right, so most of the real ones have a prediction probability that gets it labeled 1, and most of the fake ones don't get labeled 1. But let's look at more specifically what are the real names that get the highest score. So that's what this third table is. So you can see that the names that this trained model really likes are these long female names. So the name it likes best in that whole data set is Lisa Marie. And if we make this wide enough, we can see that it has 4 nines. It really likes the probability that Lisa Marie is a real name. The next little table is the names that are real names. We know from the label they're real names, but they get the lowest scores. So it really does not like some of these names. And these names are actually in the baby names database. So this first one, now when you run this, this is a non-deterministic because it's stochastic So you might get a little bit different here. But this first one, I looked it up on Wikipedia. That's a Nigerian name. There's an American football player with that name. It's a real name, but it's not very like other names. Right? It has an unusual distribution of consonants.
Can you say the name?
I cannot say it. I will not entertain you in that way. But if I were to just look at that name, I'd have to go look it up before I believed it, right? So it's the machine is kind of doing what I would do, right? It doesn't like the name Vu. I have a friend named Vu. I know that's a real name, but hey, it's only 2 letters. Got a poor score. The other one's like the next one looks like Egypt, but if you'll notice, it's got the Y and the G in the wrong place. So that's a pretty weird name. And then ZZYZX is probably designed to be a weird name. This one on the 4th row there, the name is ZZYZX. Is that your name? I'm sorry, I didn't mean to offend anybody.
I think there's a wolf is just called that in the US.
It says it's a community in California.
Well, it would be in California, wouldn't it? And there's somebody named after it. Or maybe it's named after this person. Anyway, my model doesn't like it. Doesn't think it's real. So it did detect sort of the weird, unusual names based on character distribution. Next table shows the best of the random names. So these are the random names with the best scores. And not too bad. So it did invent Jane. You know a Jane? Do you know a Kellis or a Rayleigh or a Nerian? They're not real names necessarily. I haven't looked them all up. But I'm thinking Tabian would be a good name for a cat. So these are actually fairly reasonable for real names. And then I also did a table of the best of the pseudo-gibberish names. And remember, it's ignoring numbers and punctuation. So it thinks the first name is Ja, and that's a pretty good name. And Ma and Sa are names. And it's pretty sure those are names, but they're not. Now, we could make that a lot better by having it count punctuation. Just that's like really easy. It's got punctuation, and your name probably doesn't.
Was your Engram analysis frequency of 1, 2, and 3 grams, or?
Yes, this one is 1, 2, and 3 grams.
Does it account for names that are all lowercase or somebody who's all?
It's automatically putting everything into lowercase. Just because it's too easy if you don't. Because like all the real names are properly capitalized, and the gibberish ones are not. So that would be too easy. But it does make a good marker, because when you look at it, you can tell whether it's a real name or not. Okay, so that's the task, right? And now we want to do a learning curve on that. Oh, sorry. I want to look at some coefficients first. So it's a linear model. And so not only did it make all those Engram features, but it gave a coefficient to each of the features. And we can examine those coefficients. So we just run the regular coef function on that fitted model, and we look at the top of it, right? And it turns out that in this object actually sorts its features by the absolute value. So okay. So this is what it came up with. Having mouse problems here. So these are the top features by absolute value of the coefficient. So it starts out with the bias, and then it says that it doesn't like Q. If you have a Q in your name, it's going to mark you down for that. But it does like QU. So remember, this is a linear model. So if you do have a Q and you actually have a QU, you're going to get marked down for having the Q. So you have to get enough extra points to make up for it with the QU. And you can walk through some examples like that and convince yourself that, yeah, it's really a linear model. So just a couple simple things like SAS. It really doesn't think that's a real name. And the problem with that is that's a common sequence in my pseudo-gibberish thing, because they're right next to each other on the home keys. And so I get a lot of SAs, SASs in my pseudo-gibberish set.
Nothing to do with R versus SAS.
No, it's completely because the A and the S are next to each other on the keyboard. I'm not poking fun at the competition here or anything. Okay, so it's you could look through that and convince yourself that it's really just a linear model based on those features. And the other thing I wanted to show you, if I can figure out how to scroll, we can do all these little tabulations. When I decide, again, because it's non-deterministic, I don't always get the same answers, but you can go look up the frequencies of the I's and the frequencies of the II's. And it turns out that I is underrepresented in real names, but II is relatively overrepresented compared to what you would expect just from the I frequencies. No, I'm sorry, it's the other way around. I is overrepresented in names and II is underrepresented. And so those you can convince yourself that those coefficients actually make some sense by doing these little tabulations. Okay, now we can talk about learning curves. So this learning curve library file defines a function that I'm basically going to use to wrap all the learners so that I can make training set be a parameter, training set size. So basically, it's going to be a floating point number between 0 and 1 that says how much of the available training data are you actually going to use. And then we can scan over it and make a learning curve. So a few decisions we have to make. So the reason I did that is that I'm sampling this training set dynamically so that you don't have to go ahead of time and make all these files with the different sizes of training sets in them. Because you notice that because all of these algorithms are designed to work with arbitrarily large data, so data that might be bigger than your memory, you end up using your file system a lot. So even in those preliminary tabulations of the predictions and things where we wanted to get the best pseudo-gibberish names, so that process, if you want to do it in a, pretend that this data set is too big to fit in memory, we have to pretend because this data set actually does fit in memory. So the easy way to do it would be just load it into a data frame and pull out the parts that you want and count them and sort them and things. But if we're pretending that it's big, then we can't load it into memory and we don't want to sort it. All right, so for this, I had to take all the predictions. And first, we take that training set and we make a score for every example. And that's what's in the predictions file. Then we take the predictions file and we filter it and we pull out just the real names with their scores. And we pull out just the random names and just the pseudo-gibberish names. And then we go through and we want to say, what's the worst scoring real name? So we load up the real names, we look at their scores, we use this RX quantile function to figure out the distribution of the scores. We figure out where the bottom 1% is. We take all the names that fall in the bottom 1%. We haven't sorted anything yet. But now those, let's assume that that's now a small enough sample that it will fit into memory. Then we load it into memory and sort it. And then I can give you the bottom of the bottom, right? So doing all that, just to make it so that it could scale, we end up with a lot of files on the hard drive. So the normal way to do these things uses the file system a lot. I'm trying to avoid all that in the learning curves things. So all of the learning curve function, that wrapper function, is going to dynamically sample from the one data table file. So it's going to pull out 10% or 20% or whatever you told it to do of the training set, and it's going to fit a model on that. It's going to evaluate the model. It's going to figure out the score for that model, and it's going to return the results and not write anything on your hard drive. All right, so you have to make some decisions when you run this. You have to decide how much of this, because we're going to do cross-validation inside that data table set. You have to decide how much of that do you want to hold out for the internal cross-validation. Because remember, we want to do the training error and the cross-validation error. So that's what this k-folds parameter is going to.
Are real names part of your holdout?
Yes, everything. We're going to take all the cases in in the training set, and we're going to mark them as being in set 1, 2, or 3. And we're going to hold out set 1, or set 2, or set 3. We're going to hold out one of those sets and train on the others. So we could do up to 3 variations.
Now up to 30% of the real names are being held out.
30% of the real names that are in the training set. So I also have this test set that when I'm all done, I have another test set that it's never seen before. But when I do my learning curve, I'm only doing it on 70% of the stuff that was in the 70% that went into the training set. Now all this subsampling and stuff is done by controlling the random number generator. So I have this this number that I call salt, which we're going to add to the random number generator so that I can run the whole thing with completely different randomness by changing the salt. And then I have to calculate what's the maximum training set size, approximately. What's the maximum training set size that I would do, right? It's going to be 2/3 of the data, so I need to estimate that. And then I'm going to make a set of different sizes that I want to try that are equally spaced on a logarithmic scale. So I've got a little function that does that, and it needs to know like what it should go up to. So now the rest of the things we need to decide whether we're using a real cluster or not, because if we're using a real cluster, we can do a lot more jobs and scan over a lot more possibilities. So if we're using a real cluster, which I am and you're not, we're going to scan over a larger number of L1 weights. We're going to try some different parameters here, and we're going to scan over some of these L2 weights. If you're just doing this on your own single node, then we're only going to scan over the L2 weights, and we're going to cut back on some of these other things. Like I'm going to do up to 4 grams, and you're only going to do up to 3 grams. So this function get training set fractions is the one that just figures out those evenly spaced training set sizes on a log scale. Now there are a variety of different learners. We're only using this RxFast linear, but if we wanted to use a different one, we might want to pass in some other parameters that are specific to that learner, but we're not going to vary them. So I just have a little list of those things here. The other thing I want to scan over is the Engram length. So I want to see what happens if we just have Engrams of 1, see what happens if we have 2, all the way up to 4. So I had to have a little function to generate those calls to featureize text using different Engram lengths. So I did that with 4 different Engram lengths. So that's ML transforms here is a list now of 4 different specifications of ML transforms, and the way they differ is in the Engram lengths. All right, so now, does everybody know what expand grid is in R? So you know that R users hate to write loops. So expand grid basically takes a list of options and it does all the cycles through that list and makes it one big table. So we're just giving it this list of the things that we want to vary over in this big grid search, and it's going to make the grid for us. And this is, once I run it here, it's going to do all that and then show us what the top of that parameter table looks like. So now we've made this enormous table that specifies every row in that table is a specification of one of the jobs we want to do. So this one only has 48 rows in it, but the one I'm doing on the cluster is bigger than that. And you notice that it's scanning over this a set of different training fractions, so it's going to span over a bunch of different training set sizes. So all of those sets of parameters are in a table. We need to turn that into a list, and then we're going to pass the list to our function that handles all the job management. So we just scan over all the rows in that function and generate a list of the different parameter sets that we want to run. And we're also going to set the compute context. So remember from Mario's talk, we can change our minds about where we're going to dispatch the computation to. So if we're working on a local machine, we would use the local compute context. And in this case, we've got a couple of different Spark options to choose from, so we're going to send it to one of those Spark options or the other. And finally, we really run all those jobs. So this particular block, because this will take about 5 minutes to run on a single node cluster. So we don't want to spend that 5 minutes twice, because once we're all done, I want to go back and knit the whole document so we get everything into a nice R Markdown document. So I'm going to manually cache those results. So I made a little file called training results, and that's where I'm going to save the results from all this, doing all these jobs. So if that file already exists, I won't recreate it. So when we go back and knit the R Markdown document, the file will already exist, so we won't have to spend this 5 minutes again when we do that. So the first time through, we're going to farm out all those jobs in that list of parameter sets using this function rxexec, which it already knows what backend has been registered. So this is very similar to the open source for each function, where you register a backend, and then when you call for each, it sends it to that backend. So, just historical note, for each was actually written at Revolution Analytics, which is where this came from. So this is like the enterprise version of for each is rxexec. So run training fraction is that function that I wrote that wraps the learning algorithm so that it takes training set size as a parameter, and it runs all the evaluations, and instead of returning a model, it returns the evaluation of the model. All right, so that's going to take a little while to run. So let's flip back to the other machine that I started at the beginning. So this is the machine that's running on the real cluster, and I gave it a little bit bigger version of that job. And you can see all the differences are in that little if block that's controlled by am I using a cluster or not. All right, so we've echoed all the code here, and we can see the results. And at the very end, we just run a little bit of dplyr and ggplot to plot it. So what you're going to get is just a 2x2 grid, and I've got a little bit bigger grid, and also my Engram lengths go up to 4 instead of 3. Now, I do have to, because this is KDD, I have to make a little disclaimer here that you don't really want to optimize parameters on a grid. So, right? So smart people don't do this. So you'll notice, look at the middle column here. That's for a particular setting of the L2 regularization penalty. And the rows are all different settings of the L1 regularization penalty. But that middle column, they're almost identical, right? So the L1 didn't really make any difference at that value of L2. So this kind of illustrates why you don't really want to tune hyperparameters on a strict grid. You always want to jitter them a little bit. Because here we've basically got the same exact results 3 times. And for actual hyperparameter optimization, you don't want to do exactly the same thing every time. Because you get into these situations where one of the parameters might have made all the difference, and you're just doing it over and over again. Whereas if we had jittered these a little bit, we would have given the system the opportunity to stumble on something that worked better. Right? But I'm not strictly just trying to look for the best parameters here. I want to have this nice grid so I can compare what went wrong here. And in this case, it's revealing that if we get L2 set too low, then in the bottom row there, we lose a lot of performance when we have L1 set to in this case, the highest value. So there's like this interaction between the L1 and the L2. And I just want to see that kind of stuff. That's why I do it on a grid. So then this last diagram shows a little zooming in on the best performing cell from that grid. So I'm using, because this is a binary outcome, I'm using AUC as my error function. And unfortunately, this whole recognition of real names versus gibberish names works so well that I'm getting really, really high AUC values. They're getting really close to 1. So I have to really zoom in to see it. So that's the bad news, is I really have to zoom into the AUC values. But the good news is I can still have measurable differences. I can still see the differences here. So you can see that only at the higher training set sizes are the foregrounds starting to show their stuff, right? So if we don't have enough data, the 3 grams and the 4 grams pretty much work the same. But once we start getting more data, once we get the whole million rows, then there's a measurable difference there between the 4 grams are starting to show that they can do a little bit better. Although there's not a lot of room for improvement, we can still measure it. Okay, so now I want to go back and show you a couple more slides. Oh, sorry. Let's do this. All right, one more slide, then I'll stop. So I went back and did an even more fine-grained comparison of the effects of L1 and L2. And so now I want to show you this the surface of error. Instead of plotting the error as a curve, I want to look at it from the top, where every column shows a scan across training set sizes. So every row shows a single training set size where we're varying the L2 regularization penalty. And we can tell what the error is by the color. So in this case, the lowest values of error are they're actually yellow. I'm sorry, I didn't get that on the scale, but those are the lowest. The lowest AUC values. Now, because all my AUC values are squashed up against 1, I had to enhance this image, and the way I did that was by, instead of trying to match the color to the AUC, the area under the curve, I matched it to the negative logarithm of 1 minus the area under the curve, which is PAOC. So P, like in pH, is a negative logarithm. Just gave me prettier colors. All right, so this is just for the n-grams of 1. You can see that for the small training set sizes, you get this little hump of better performance. All right, that's kind of hard to see on the screen. But let me go to the next version, which is the Engrams of length 2. It's a little more dramatic. Right, so we see that L2 needs to be tuned for those. If you look at the top lines, there's an optimal value there for L2. Where if we don't regularize it enough, we don't get as good a performance. If we regularize it too much, we don't get as good as performance. But there's this Goldilocks happy medium there. And then as the training set size gets bigger, we see that L2 regularization optimum moves. So for the bigger training set sizes, we actually don't need as large of a regularization penalty, L2 penalty. So just a way to visualize the interactions there. But so every one of these cells in this grid has been a different job that I sent out to my cluster. And I sent a whole set of them out for the n-grams of 1, a whole set for the n-grams of 2, a whole set for the n-grams of 3, a whole set for the n-grams of 4. So just an example of something that you might want to use a cluster for, where you have it's basically an embarrassingly parallel problem. I've got a lot of little jobs that I want to do. And so this is an approach for doing that. All right, so that's all I've got. I'm going to turn it over to Vanja. But Vanja is going to show you a smarter way to do a bunch of little jobs.
Okay, can you all hear me? It sounds like it. Okay. So? Okay. So I'll be continuing with another sort of toy scenario for scalable data science using R. And this problem of group time series forecasting came about while working with a customer who had this group time series data set that we were trying to forecast. And so initially, what we were doing with it is we were basically trying to optimize the forecasts by running over all of these different algorithms and their parameters, essentially doing a parameter sweep for group time series forecasting, and we were trying to do it in an efficient manner. So initially we were doing something like what Bob showed you. We were using HD Insight cluster to spread out jobs on multiple nodes. Even though this was not a big data job, this was a high computing or just embarrassingly parallel job of many processes on small data sets. So what I'll show you essentially is how to do this parameter sweep on a platform called Azure Batch, which is a batch of VMs that you can spin up really quickly on Azure at a really low price as well, that allow you to just spin up a ton of, like tens of thousands R processes for really quick parameter sweeps. So just to give you some background on this problem, group time series forecasting shows up when time series data can be disaggregated into by many attributes of interests to form these groups of time series or hierarchies of time series. So for example, on this picture, we show that, for example, we can forecast if we have a data set that contains information about many customers, about their many products, about their many locations, and so on, we could forecast that data in aggregate overall. We could disaggregate that data to only look at the time series by customer, or we can even further go and disaggregate that data by customer, product, destination, and so on. So the issues that come up when forecasting group time series data is that forecasts that you produce at these different levels of hierarchies or hierarchy or groups have to be consistent. So when you forecast at the total, that number has to be the same as if when you forecasted, for example, at the customer level and then added that up to the total. If you did this independently, it wouldn't necessarily be true. However, there is a set of forecasting algorithms that are specifically designed to handle these group time series, which essentially forecast the time series so that all of the produced forecasts at all of these levels are consistent. So I'm not going to go too much into this because this is not the focus of the talk. I just wanted to show you, to give you some background on what we're doing. And this is the example data set that we're using in the tutorial. In the hands of, yes?
I don't quite understand why those individual forecasts don't add up to the aggregate one.
Because they don't necessarily add up to the aggregate. And they're actually not very likely to do. So if we, let me actually go to this table here. So this is an example data set. So if we now, so now for each of these customer and for each of the products and for each of the destinations, here we have a time series. So now if we produce the forecast for each of these separate groups, we get a set of numbers. However, if we now sum up these numbers and have just a single time series of over all of these variables, we're going to have a time series and we're going to produce a forecast. Simply because these are estimation, these are estimation models. The numbers that we produce are not going to be probably the summation of the numbers that we produce, simply because of errors, right? You get errors when you produce any sort of estimate. So you're it might occur that they add up, but it's not very likely. Does that answer your question? Mm-hmm. All right, so in these couple of slides here, I'm just showing different ways of doing these hierarchical time series forecasting, where some methods sort of start at the bottom, forecast at the most detailed level, then go up and aggregate the forecasts to obtain other levels. This is called bottom-up approach. The top-down approach goes from the top and produces a single forecast over all categories. And then simply using historical proportions available from historical data, it disaggregates the forecasts. And ultimately, there's a middle-out approach that sort of combines these two. So let's go to the code and look at what we're doing here. So the code that we'll be looking at is in that same KDD directory under code, then under grouped time series. And you might not see all of these files. You actually are not seeing all of these files. So you don't have the cluster and credentials.json files at your end. And I'll explain why that is. So what this code, you can open this function main.r. Yes?
Expand the font a bit.
OK. To expand the request to expand the font. Let me see.
Just a control plus
Should work. OK. Is this better? OK. All right. So what we're going to do, what this code does is ultimately takes that sample demand data set and runs over a number of forecasting algorithms and parameters to do a parameter sweep in order to produce the best forecast. So the main function is here in main.r. Most of the other functions are in forecast utils and params search utils. So let's open this params underscore search underscore utils. So this is really where most of the work gets done. Let's minimize this one. It just produces the power set of the variables. All right, so here is the main function that runs over all of the algorithm parameters. In fact, in this problem, we have a very small parameter space. It ultimately contains a Cartesian product of these variables here, or these vectors here. So it's not very big. It's about maybe 8 to 10 combinations. However, what I wanted to show you is how you can distribute these jobs on a parallel backend by simply using a popular for each package. So if you're familiar, you might have used for each package. A lot of people have, but it's simply written for distributing parallel jobs on a parallel backend. If you're running it on your machine, it's going to distribute jobs on your cores. If you're running it like I am on Azure Batch, it's going to distribute the jobs onto the nodes that are available in the Azure Batch. So for that, I am using a package called do Azure Parallel, and this is what Bob mentioned is really cool. It basically allows you, this package is written to complement this set of parallel backends to the for each package. So you can simply install this package on your machine, create an Azure Batch account, which is free, and then simply use this very small set of commands to create pools of VMs, run your function, whatever R function you defined at your end, run your function in parallel on the pool of VMs that you created, and after you're done, you can delete the pool. So I'll show you how that's done here. All right, so this is my Azure Batch account. As I said, Azure Batch is a free service. What you're paying for is the pools of VMs that you create. So I have 2 pools of VMs. They're both actually really small because I wrote them just for this, created them just for this toy problem. But so we're using this my Azure pool that contains 4 dedicated nodes and 4 low priority nodes. Now. And you can see all of these nodes here. So 8 nodes in total, 4 dedicated nodes, and 4 low priority nodes. What's really cool with the low priority nodes is these are essentially Azure nodes that are sort of idle, and you can provision them at 80% discount versus regular VMs, with knowing that they can be taken away at any time if a higher priority task shows up, but that they'll be brought back after the higher priority task is finished. So it's sort of a cheap way of distributing your jobs that are not of high importance. So if you're waiting for something to be done overnight, you can use these cheaper nodes to do the task. So let's run the code here. So if you go to main function, you guys can can leave the run local to true because you can execute these commands in your local VM that you're using. I have an Azure Batch account created, so I'm going to be using an Azure Batch and change it to false. All right. So this is just setting, loading the functions that I'll need. This is setting the run local to false, meaning I'm going to be running it on Azure Batch. And this is simply defining some variables that I need to export to the nodes, to the VMs that I have in my pool. This is reading the data set. OK. And so when I execute this huge if-else statement, you will be seeing the execution of this chunk. So what it's essentially doing here, it's loading do parallel, which is the parallel backend, or the package that sort of uses for each to do parallel computation. It's creating a local cluster, which basically is a cluster of cores on your machine, registering it as the parallel backend, parallel compute backend, and running the function that I wrote for the parameter sweep.
Do you recommend it do parallel or do you do MC? Which one do you recommend?
So I think the question is if I recommend do parallel or do MC. Yeah, I think Mario actually just mentioned that they are merged into one, do parallel. Yeah, so do MC is now do parallel, merged into do parallel. So do parallel is more up to date, I suppose, so I would prefer that. Yeah.
Did you mention that we should set run local to true?
True, yeah.
So we're going to be using the other parallel code.
What was the question?
So if you put false, then we're going to use the other section.
So I will be running the other section because this is the section that uses Azure Batch. But yeah, otherwise, basically, if you run it as false, you'll get an error on your end. So let me show you here what it's doing here on the Azure Parallel end. So I'm loading this do Azure Parallel library, which is written specifically to utilize this Azure Batch capability from R. So here's a link to the do Azure Parallel package. It's got really nice documentation, and it's really useful for working from R with Azure Batch. The two files that you need to be working with Azure Batch from R, from your local R session, are the cluster.json and credentials.json. Credentials.json is simply a number of credentials that allow you to interact with your Azure batch. However, the cluster.json is really a file that lets you define your Azure batch pool. So I am naming my pool my Azure pool here. I am selecting a VM type that I want to create a pool of. There's a whole list of, I don't know, 20, 30, something like that. Pretty much any sort of any VMs available on Azure, you can create a pool of, and you can create a pool of 10, or you can create a pool of 10,000. It's pretty neat. I'm selecting four dedicated nodes here and 4 low priority nodes. The min-max values allow you to auto-resize your pools. So while you're running high-intensive jobs, it's going to provision for the max number of VMs. When you are not running high-intensive jobs or when you're idling, it's going to resize to the minimum number of nodes, so allow you to reduce the cost. Because these VMs are charged just as you're using them. And then finally, you can pass any packages that need to be installed for your R script that you're distributing on these VMs. So I am, I'm making usage of these 4 packages during my parameter sweep. So I'm making sure that they are installed on these VMs that I'm provisioning. And so I've already created this pool because it takes maybe 5 to 6 minutes or so for the pool to be created. So when I run this cluster make cluster, it's going to just let me know that I already have that pool. The specified pool already exists. We'll be using the existing pool. The set credential commands simply sets the credentials that you specified in your credentials.json file so that you can interact with your Azure Batch account. What else to note here? So all of these functions generate cluster config, generate credentials config, set credentials, make cluster, and so on are a part of this do Azure parallel package that allow you to so easily work with Azure Batch from R. So to see that this command lets us register Azure Batch as the parallel backend. So once we have Azure Batch registered as a parallel backend, the for each loop is automatically recognized it as a parallel backend. And so anything you put within for each is going to be executed in parallel on the VMs on the Azure Batch. And then finally, this is the function that I am running in parallel. There are some warning statements that are printed out. You can ignore them. This is going to take a little bit, so we don't have to follow it. We can go back to slides, and we can come back to this once it's executed. Does anyone have any questions in the meantime? Yeah.
In this moment, dataset is transmitted.
Yes, I actually wanted to show you that. Thank you for pointing it out. So this is my Azure pool. Currently, as you see here in this legend, they're all idling. Soon, all of these nodes are idling. Soon, they'll be showing up as green, which is basically means a process is running on them. Now let me just refresh. All right. Yeah. So now all of these that are green are running here as shown in this legend. For example, right here we have 4 low priority nodes running. And this is 80% discount, I think, from the regular priced VMs. So if you have a low priority tasks that you don't really care about when they would be done, like a parameter sweep that's not urgent, you can spin up hundreds of these low priority nodes and do a parameter sweep if your parameter search space is really large. And while this is running, we can see some output here about the status and how far the execution is. All right, so this is going to be done pretty soon.
You run it through a JSON file, but in here, there is no JSON file.
Yeah, so I didn't, so as I said, you will be running this code locally. So I did not create Azure Batch accounts for all of you. You have to create your own Azure Batch account and then create a pool on it. These cluster.json and credentials.json files specifically relates to the Azure Batch account. You can still run this code, but just make sure, or just leave this run local as true right here. Or change it to true. I'm not sure what versions you had.
Just a clarification for me. You're not using any Microsoft libraries specifically for the algorithms, right?
Yeah, no. Do Azure Parallel is written by a Microsoft employee, but it's open source. Yeah.
But the forecasting algorithms, you're using other.
This is all open source. Yeah. For the forecasting, I'm using the HDS package. Yeah, and so I'm also passing it here to the VMs. Yeah, everything else is written in open source R. It's just the compute platform that I'm using is Azure. All right, so yeah, the parameter sweep is done, and it's telling us that the initial best score was 7.24. This is in root mean squared error, and that the optimized one is 5.87. So it's sort of, and this is a small problem, but it's sort of in quick time it gave us, it ran through all our parameter space and found us a set of parameters that we could use to obtain the optimal forecast. So that's all I have on the group time series forecasting. If somebody has more questions, I can answer them now or after the talk. All right. So in that case, I'm going to move to another use case, and that is sentiment analysis with pre-trained deep learning. So we were talking about the scalable data science in R, and so a lot of people are doing deep learning these days, and we were thinking of ways on how to also introduce scalable deep learning in R. And I just wanted to cover first, we're going to be using it as through this use case, sentiment analysis with pre-trained deep learning. So ultimately, we'll be loading a data set of movie reviews, and we'll be computing sentiments for those movie reviews. Were they positive or negative sentiments using pre-trained deep learning model? I just wanted to have this as put this as a material that's available to you afterwards. I was looking into options for doing deep learning in R in general. And so this is a table showing what's available today. Most of this is probably familiar to you: TensorFlow, MXNet. These are the frameworks, deep learning frameworks that now also have R APIs. And so the network architectures covered through these APIs are pretty much all of them. In this case, feed-forward neural nets, convolutional neural nets, recurring neural nets. Most of them are also CPU and GPU enabled. So if you have a GPU on your machine, the acceleration is natively supported. And these are just showing Tensor backends. So TensorFlow and MXNet are APIs that are simply APIs for the TensorFlow backend and MXNet backend. Keras, however, is our API that is our interface for Keras, which is a Python library that allows different tensor backends. So you can, through Keras, you can use TensorFlow as a backend, you can use CNTK as a backend, and Theano as a backend. So you can use these different deep learning tools through a single interface from R. H2O has another a cool set of products for doing deep learning in R. Their initial, I should point out that the second option here, H2O .deep learning. So both of these packages are called H2O. The different functions are H2O.deep learning and H2O.deep water. H2O.deep learning is the initial version of the deep learning capabilities within H2O, but they only allow feed-forward neural net architectures. And only CPU as the platform. The H2O.deep water is a new product, and it might still be in beta, or it might be very, very recently released. But H2O.deep water is a more comprehensive backend. It uses different tensor backends, TensorFlow, Caffe, and MXNet, and it can use CPU and GPU. And finally, Microsoft ML. Mario talked about Microsoft ML. It's a library that's available through Microsoft R Server that has a number of cool machine learning algorithms as a part of this library. These are as Mario said, these are battle-tested machine learning algorithms that are basically deployed widely within Microsoft. And so Microsoft ML is the one that I'll be showing you today. It has feed-forward neural net and convolutional neural net architectures. Recurrent neural nets can also be used, but it's a little bit trickier, and it's not super natively supported. You have to do a little bit more work around it. And then finally, it has both CPU and GPU acceleration. So let's look at this sentiment analysis example. So if you go into code, sentiment analysis, and then movie sentiment.r. So what we'll be doing here is, all right, let me do this, is we'll be loading a data set of movie reviews. So this is 50,000 movie reviews that are highly polarized. Some of them are highly positive, some of them are highly negative reviews. So they have ratings 1 to 10. And what we'll consider a positive sentiment are ratings higher than 5, and negative sentiments are ratings lower than 5. So these initial commands, I'll run through them quickly, but they're essentially just downloading the dataset and processing it. So I'm just going to select all of this and run. And then finally, we're doing splitting here of the overall dataset into training and testing. So what we want to do, what we're going to do in this data set is finally obtain the sentiment score for each of the reviews in this data set. So this is already available. We're not going to be training a deep neural net in this example because this is already available within this Microsoft ML library. So Microsoft ML library has a function called RX Neural Net that allows you to train neural nets and define their own architectures or your own custom architecture. However, it also has what we call cognitive services APIs to already pre-trained, highly pre-trained or very good neural nets, deep neural nets that are trained on very large data sets. So they're very good. Or very good for specific scenarios, I should say. So there are two cognitive services APIs that are available within Microsoft ML. This is the get sentiment one, the one that we're using here, which is basically a neural net, deep neural network trained on large corpuses of text data to obtain sentiment from any English sentence or phrase or text. Another set of cognitive services API is for image featurization. So it's a deep neural net that basically can create features for your images so that you can use them, for example, to compare images, to look at their similarity and so on. So when you invoke one of these functions, what's happening in the back end, it's really just using a saved model of deep neural net to obtain these scores, to run your data through these deep neural networks and obtain the scores. So the first thing we're going to do here is we're going to run two models. One model is just going to use Engram features on these text data set. And Bob talked a little bit about Engram features. So it's just going to create Engram features from these movie reviews. And then we're going to train a model on those features. In another scenario, we're going to be using Engram features plus the sentiment score that we obtained from the get sentiment function, from the deep learning model. So we are doing it all at once here using this ML transforms parameter here, or argument, that allows us to featurize data allows us to create sort of different kinds of features within one function. So we're running 2 times for training and test data set here. So as I mentioned, we're going to be having 2 models. One is trying to estimate the sentiment of a movie review based on just the Engram features, which we call review TRAN here. And another one is estimating the sentiment of a review using the Engram features plus the pre-sentiment that we obtained by invoking the deep learning model. So our data is just getting featurized here, so it's going to take a little bit. So once we have these 2 models, we simply run logistic regression to obtain sentiments, and then finally we're going to score the test data and plot the ROC curve. What we're trying to do here with this code is look at how we can improve our model by adding these sentiment features that are available through getSentiment function. So if you can also, what we could have done here actually is we could have used that sentiment as the final label as well. So if we didn't create Ngrams at all, but just run our movie reviews through a getSentiment function, it would create a sentiment score. So we could also just use these scores as the final label. But I don't know why I didn't do that. Here, it's going to be neat to see though how we can improve on what's traditionally done is simply computing sentiments from these Ngrams or adding this additional feature to it. All right. Does anybody have any questions in the meantime? While this is running.
So the first model just gives you the sentiment score, and the second one gives you the score for recommendation or something?
No, so both models are trying to compute that sentiment score. Okay. Yeah, so both models are logistic regression that is going to produce the sentiment score for your movie reviews. It's the difference in the features that they're using. So the first model is just using the Ngrams that are computed from the text. I should point that out here in the code. Max featurized sentiment. Okay. All right. So featurized text here is a transform that we are applying on our data to produce the Ngrams from a movie review. So what it does, it basically looks at, the function basically picks out the most important Ngrams of the movie review, and it sort of creates a set of features from those Ngrams. So if you just had those Ngrams and feature, in your features and applied logistic regression to obtain sentiment, this is the first model. The second model is going to have those Ngram features and also an estimated sentiment obtained from this getSentiment function. So just one additional feature, and then we're going to be applying logistic regression on that set of features.
And the output of second model is again sentiment?
Yes, yeah. So that's why I'm saying you can also use getSentiment to directly obtain the sentiment without Ngrams. We're just sort of trying to even further improve by including these.
And the Ngrams is like n is changing, it's just, or n is constant?
Actually, I'm not sure in this function. I think you can define, I think this is a default, so I don't know what the default number is, but you can customize the number of Ngrams that you're getting. And whether the Ngram exists or not. So there's different types of Ngrams features that you can create. For example, you can generate the Ngrams and just have a binary feature on whether the Ngram exists or not, or you can have the TDF, IDF frequency sort of features and stuff like that.
So these Ngrams are word level Ngrams,
Yeah.
not character level.
Yeah, these are the word level Ngrams. All right.
You're not doing a continuous representation. It's not like a word effect or.
Yeah, no, we're not doing continuous representation. All right, so our data got featurized here. So let's run these two models. So we have the model 1, which is estimating sentiment just using Ngrams, and the model 2 estimating sentiment using Ngrams, and the pre-estimated, I should call it pre-estimated sentiment using the getSentiment function. And we're actually great on time. It's 5 o'clock. We will be done really soon.
I just want to mention that you can type question mark and featurized text for more details.
Yeah. Okay. So we can do that right now. Mario mentioned that you can just type question mark and the what's the function, featurized text, to obtain more information on this featurized text function. So this. This will give us here sort of docs for this machine learning transform. So you can look up the n-grams information. All right, and then finally, we have our models. Let's score the data, the test data, and let's plot the ROC curves. I should point out, and we're not going to be running here now, but what we did ultimately is we ran our scoring on the test data in a non-parallelized fashion. To parallelize scoring, you can enable parallelized scoring by running the rest of this script. Ultimately, what you need to do is chunk up your data into smaller data sets using this XDF type of format that Mario talked about. And then after you do that, you can define your scoring function within a single function. And then finally use, so we're just opening a Spark connection here and so on. And then finally use RxExec that Mario used in his, did you Mario use RxExec? Yeah. To parallelize your scoring function on the different data sets that you created. And I urge you to try this if you have time today on the VMs that we provided for you today. And then finally, let's look at the ROC curve. So if you think of the get sentiment function, this is weird, okay. All right. Let me do this. So if you think of the get sentiment function, just another featureization function. So ultimately what you're doing is creating another feature from your text data. So n-grams is a set of features, and then the get sentiment function runs your text through a deep learning model to produce one more feature. So if you think of it just as a featureization function, that's ultimately what it is. So if we add that one feature here to our model, we get improvement from 0.93 AUC to 0.95 AUC. And in some applications, improvements like this is very significant by simply including that one feature into our model. All right. And this is all I have for you today. Does anybody have any questions on group time series or deep learning in R at this point? Yes.
What's the limitation for deep learning with the Microsoft server solution in terms of really deep network? Do I run out of memory?
Probably yes. This is why, but that's true for any deep learning frameworks out there. And this is why most of them have the GPU acceleration that allows you to, even multi-GPU acceleration that allows you to have these big machines, GPUs.
Do I have to choose the machine type for the Microsoft ML?
For the Microsoft ML is a separate product. It's not a machine. So you can run Microsoft ML on ultimately any machine. So when you're provisioning, are you basically asking what Microsoft products are available for running deep learning? Or
Maybe I misunderstood, but I thought like with Microsoft ML, I configured via R and then push it to the Microsoft Cloud solution.
What you could do is with Microsoft ML, you can provision a GPU VM on Azure, and then write your code wherever on your local machine or on that VM, and then do the training of your deep learning network. If you have a very deep network or a big data set, do the training on that GPU accelerated machine. So anybody who's developing any serious deep learning network is using GPU acceleration at this point.
Could it be used with Spark R?
Microsoft ML, I suppose, Mario, can it be used with Spark R?
It could be used with Spark R because Spark R can run any R functions as user-defined functions. So yes, you could use it together with Spark R.
Yes. All right. So I just wanted to remind you of two other things. The tutorial that we had at the beginning on SQL Server, our services within SQL Server, the scripts are currently not on GitHub, but will be available on GitHub by the end of the day. And that material is going to be there on that GitHub forever until GitHub allows us to keep it there. And another just announcement, there's another tutorial tomorrow on cloud-based data mining tools. It's at 9 a.m. tomorrow, and it's essentially data mining on Azure. They're going to be going through IoT scenarios, through some scenarios using Cluster HD Insight. But what's cool about it, I think every participant is going to get a $500 Azure subscription. So you can then use it to test out any other Azure services that you're interested in. And this is all I have all we have for today. If you have any questions, we'll be sticking around and you can talk to us. And thank you for your participation and your patience. This was a long tutorial.